This is the first part of boundary value problem video. In this video I'll be talking about how we can discretize and solve boundary value problems using finite difference methods. So in boundary value problems, as it stands, we have boundary values on both sides of our domain. If you think of it 2D, or maybe 1D if you will, then we have boundaries on the left and on the right side. If we have boundary conditions all on one side, that problem is called initial value problem. In this part of the lecture, we're going to look at two different boundary conditions. One is when the function value is given at one boundary or one boundary point, and then the second condition, or the second type of boundary condition, is where the derivative of the function is given. So the first one is the function is given, the second one is the derivative of it is given. The first method we're going to look at is called direct method of solving boundary value problems, where we directly discretize the differential equation. So here we're going to look at the first linear second order differential equation. It's linear because there's no nonlinearity in any of these three terms. It's a second order differential equation because the highest derivative is 2. We have two boundary conditions. At point 0 is 10, and then derivative on the other side at point x equal to 0. So we're going to go ahead and discretize every term. For the first term, we can use central difference. And just to remind ourselves what this is, we're going to go to the page I uploaded on the website a long time ago. That's on derivative or the discretization of the derivatives given the order of approximation. So if you think of second order approximation, we go to the central difference, and we're going to pick up the bottom formula here, which is the second derivative discretization, fi plus 1 minus 2fi and fi minus 1 divided by del x squared. We're going to go back here and then replace the first term by the 3 point stencil. 3 point because there are three terms here, and it's relating I plus 1 to I and I minus 1. Okay, so that is replaced by the second order approximation. We're going to go ahead and do central differencing on the second term. We're going to go back to here, and so here's the central difference version of the first derivative, I plus 1 minus fi minus 1 divided by 2 del x. Here I have replaced this term by the discretized version of it. And then the last term is just itself. So again, every term is discretized at point I. This is at point I. This is centered at point I. And this is also centered at point I. We use second order central difference for this piece, which is this one. We also use second order central difference for that piece, which is this one. We reorder the terms. We group I plus 1 term, I term, and I minus 1 term. So from here to here is just a little bit of math and reordering the terms. Now we're going to plug in I starting from 2. So if we put I equal 2, then the minimum index is 1, where y1 corresponds to the boundary condition on the left. Okay, so y1 is the boundary condition on the left, and then yn is the boundary is the y value on the right. So anyways, we start from I equal 2, then we get we're going to start from here, then we get y1 times 1 plus del x. This term is y2 times minus 2 minus 10 del x squared, and this is y3 times 1 minus del x equal to 0. So from these three terms, when I is equal to 2, only this piece, the last term, is known because y1 is the boundary value on the left. So we're going to move it to the right side. And then we put that equation into a matrix form. So here's our matrix form. The first line of this equation is exactly the equation we just talked about. So if you multiply this row by this column and equate to the first element of b vector on the right side, then you would get this equation where I is equal to 2. Okay? So note that for this equation where I is equal to 2, we only have y1, 2, and 3 involved. y2 and 3 stay on the left side of the equation, because if you multiply this by that, you would see it. And then y1 goes to the right side because that's known. Now if you plug in I equal to 3, then you have y2, y3, and y4. That constitutes the second line of the equation here. Okay, so we get the first and second and third column exactly corresponding to y2 here, y3 here, y4 coefficient. And because nothing is known here, the minimum y we have is y2, and y2 is unknown. So then the second equation doesn't have any right term. So the b element here is going to be 0. So anyways, we can keep adding or increasing I from 2 all the way to n minus 1. So for the last I index, the maximum y index we get would be yn. And that's what we have. The next to the last equation here is corresponding to I equal n minus 1. So if you multiply this row by that column, you get this equation where I is equal to n minus 1. So note that this matrix so far is a tridiagonal. All other elements on both sides is 0. Now, so we took care of the boundary condition on the left. The last term we need to take care of is the right boundary condition, which is of derivative type. So that's the second boundary condition we have to discretize and put that into the matrix equation here. So that condition, dy dx equal to 0, also can be discretized, but not using central difference, using backward difference, because if you were thinking of the right boundary condition, everything on the left side of it is known, and on the right side of it we don't have anything, because that's the end of the domain. So instead of using central difference for the derivative to impose boundary condition, we're going to use backward difference. So here's the backward difference that I grab from here. If you go to this table, that's the second order approximation, same table we used for central difference, but now we're going to use backward difference form for the first derivative, which is this formula, 3 minus 4 plus 1 divided by 2 to the x. Indices go from I to I minus 2. And I have the same thing here. Indices go from n to n minus 2. 3 minus 4, 1 divided by 2 to the x equal to 0, which means the coefficient for yn is 3/2, and the coefficient for yn is exactly equal to 3/2 in the last row of my matrix form. The other coefficients, minus 4 divided by 2 and 1/2, are again put down into this row. So that means now I impose my boundary condition to the last equation, where I have the last 3 elements non-zero. All other elements on this side would be 0. So this big 0 means everything on the lower left and upper right corner of my matrix is 0. So anyways, I have a matrix form. I can go ahead and use back// operator to solve it. Now I'm going to go back and see how we can use this algorithm to solve the problem in MATLAB. So here's the MATLAB script. I implemented the same problem using MATLAB. I have my domain length equal to 1, boundary condition on the left is 10, I have 100 discretized points, where it gives me the interval equal to the length divided by 99, because the 2 endpoints are included. So I create my matrix coefficient, which is now n minus 1 by n minus 1. It's a square matrix. My B matrix is n minus 1 by 1, which is the right side vector. Alright, so if you remember, in this matrix I have 3 types of rows. The first row is different because I only have 2 elements in that row. All other rows, except the last row, have 3 elements, and they're exactly the same. 1 plus x minus 2, 1 plus 5 del x squared, and 1 minus del x. So all other rows have exactly the same 3 elements. And then the last row is again different from all others because I have like 1 half minus 4 halves and 3 halves. So I need to treat assembly of this matrix using 3 conditions. That's what I have, 3 if statements here. The first one assembles the first row. The second if condition assembles the last row, and then the last condition here assembles all other rows. And for the first row, the right side is minus 1 plus del x times y naught, and that's exactly what I have here. The coefficients, the 2 coefficients are minus 2 times 1 plus del x squared and 1 minus del x. And the last row coefficient is 1 minus 4 halves and 3 halves. That's what I have here. And then all other rows have the 3 coefficients we just talked about. So anyways, I assemble my A matrix here. My B matrix only has 1 element, where I assemble it in the first part of this matrix assembly here, because my B only has the first element non-zero, all others are 0. So I assemble my B here, my A, three parts here, and so now I have my A assembled, B assembled, use backslash operator to calculate W. After you calculate W, you concatenate that with the initial condition y naught to make a vector of n terms. So before we had n minus 1, so W has n minus 1 elements, but then y has n elements because we concatenate with the initial condition. So we have y. We can now go ahead and plot y against x using MATLAB. If I run this code, you see the solution to the system, which is y against x from 0 to 1. Every dot corresponds to 1 discretized points, and you see that the boundary conditions are satisfied. The slope here is supposed to be 0, and that is exactly the horizontal slope here, and the value on the left is exactly equal to 10. So we solved the first linear second-order differential equation with 2 boundary conditions, function value type on the left point, and derivative type on the right point. So hope this was helpful. In the next video, I'll be talking about the nonlinear version of this equation, where we have 10 times y squared replacing 10 times y in our first equation. So stay tuned, and thanks for watching.